Hello and welcome to another very exciting See the Change USA webinar. My name is Vincent Weiss. I'm the manager of product and training development, and today we're going to talk about the second part in a four-part series where we cover all the topics found in Energy 1, and today we're specifically going to take a look at potential energy with a little bit of energy concepts mixed in. So first off, getting started, a few housekeeping items for this webinar. There will be no audio or video, so if you have your video turned on, if you can please switch that off now. The way we're going to communicate is using the chat box feature if you don't have the chat box on your screen, move your cursor to the top of the screen and a drop-down menu will come down. Click on the ellipse on the far right of the screen, and then you'll see an option to open up the chat box. Click on that and it'll open up, and if you have any questions at all during this session, do feel free to place your questions in there and I'll try to answer them throughout the session. This session, as always, will be recorded, so the recording will be placed both on the physics lab and within the Edmodo group, and I will show you how you can access the Edmodo group at the very end. And also the PowerPoint will be made available on Edmodo. So for those of you who are not members of Edmodo, I would highly encourage you to sign in and sign up, and I will again show you how to do that at the very end. But there's a lot of cool resources that you can find there, including the PowerPoints to these webinars. So I would highly encourage you to do that. So purpose of today is to build your confidence in physics first and foremost. As we say, you are all excellent science teachers, but what we want you to be is world-class middle school physics teachers. We want you to be some of the best. And really the aim of these webinars is to help you to get there. So a lot of the concepts that we cover will go a little deeper than they are in class, than you'll actually experience and that you'll ask your students to go, but this is the way it should be. It should be that the teacher seems to know a little more and has a little more information, so that way you can encourage your students in different areas and poke and prod and be able to give them a little bit of insight so that they themselves can soak up more information. And this is also to help you to bring high-level physics content to the middle school mind. So a lot of the things that we're going to be covering, we're going to talk about different tips and tricks and approaches and just ways to break down some of this high-level physics content so that you could actually take it and help explain it to a student using animations, using visuals, using different methods like that. So who's this for? It's for teachers looking to take their students to a deeper level of understanding. And it's also for teachers who do not have an extensive background in physics but would like to master the concepts. As we said before, you don't need to be a master in physics to understand some of these things. But if you can just understand even half of what I'm going to talk about, then you're probably more equipped than 90% of middle school science teachers. So you will be ahead above the rest. And this is also for teachers looking for alternate ways to explain concepts to your students. As we said before, we're going to have a bunch of different ways to explain these concepts using animations, graphs, and and then you kind of get an insight from the See the Change staff. So good stuff. What we'll cover specifically the content found in lessons 1.4.7 through 1.4.10. So 4 lessons from the unit Energy 1 and the See the Change USA curriculum. While we're doing this, we're going to define energy, define what it is, and look at some examples of what energy does and how it is transferred from one type to another. And we'll also explore the basics of potential energy, specifically gravitational and electric potential energy. And at the very end, we're going to have a question and answer session about the content found in these specific lessons. So without any further ado, let us begin. So energy. Energy is an extremely important topic in physics, and it allows a physicist to do a lot of different things. But it's not just important in physics, it's important in all areas of life, because if you live and breathe and live in this world, then you are affected by energy in one way or another. So let's look at this example. Here is a soccer player that kicks this soccer ball, and if we look at this ball, we would immediately see it has energy. It has energy because it's in motion. So it turns out anything that is moving has energy, and this specific type of energy is called kinetic energy. If we were to look at some principles, we see that energy cannot be created. It must be transferred from one place to another. This is called the conservation of energy, and it's one of the most fundamental principles in all of physics. So whenever we look at something that has energy, like this soccer ball, we need to ask, well, where did that energy come from? And then later we can ask, where is that energy going? But somehow that energy in the soccer ball came from some place. So this is not too difficult because we know it came from the foot. And the foot delivered that energy through a type of mechanical energy. So this mechanical energy was transferred to the ball and is now kinetic energy. But where did that energy came from? It came from her muscles. And immediately we'll notice that there's multiple types of energy in place. There's the energy it takes to kick that ball, but as she's running around and working, she's going to have thermal energy leaving her body as she starts heating up. So we need to also explain where this thermal energy comes from. And it all comes from the food that is in her digestive system. There's chemical energy in there. So if we kind of take a look at the food that she's digesting that gives her this energy to kick the soccer ball and to expel all this thermal energy all over the place, we will immediately see, well, there's chemical potential energy inside the food. All of our diet can be broken down into two categories, either some type of meat or some type of plant. And when I mean plants, that includes fruits, vegetables, breads, because breads come from some sort of grains. Even sweets come from some type of plant. So plants incorporates everything that's not meat. But if we look at some meat source, like a cow or a chicken, that can even be traced to some sort of plant. So when it comes to all the energy this girl needs to kick the soccer ball, it originates some way, somehow, through some type of plant. Well, we can go even farther. What do all plants in the world derive their energy from? Because it's actually that energy that's transformed into this chemical energy that gets eaten and is used to create the energy for the muscle to produce the thermal energy that causes the ball to actually move. So we're really asking, where does all that energy come from? Well, it all comes from the sun. Specifically, the light energy and the thermal energy, or the heat energy that comes from the sun, is what powers the plants, that powers the human, that powers the kicking of the soccer ball, that powers the ball. So that moving ball, the energy from that moving ball actually can be traced back to the sun. And most of the energy we use and we see can be traced in some way or form back to the sun. So here we have planes, trains, and automobiles. The plane and the automobile use some sort of fossil fuel, and most fossil fuels come from the decomposition of tons and tons of plants that originally got their energy from the sun. So the movement of a vehicle or a plane can usually be traced back toward the energy of the sun. And even this train, if this is an electrical train, which it looks like it could be, this electrical system got its energy from the electrical grid, which in most cases it's traces back to a plant that burns some sort of fossil fuels to generate electricity. But even if it was actually no, I guess in the small case that it's connected to a grid that is fed by a nuclear power plant, this is actually a type of energy that does not come from the sun. So this would be an example of one of the few cases where you can trace something back to something other than the sun, because the nuclear energy that a nuclear plant generates its energy from comes from some other source other than the sun. I don't have time to get into it, but this would be one of those few cases. But most likely, all of these sources get their energy somehow from the sun. Oh, so up till now, I've kind of described energy and how it seems to kind of move from one thing to another thing, but I've not really described precisely what energy is. So energy does one thing. Energy describes matter's ability to do work. So energy enables something to accomplish work. If you saw our previous webinar, we defined work, and we said that work describes how much effort it takes to either speed something up or move something against a force. So we stress that word effort, but as it turns out, you can really replace that word effort with energy. Work describes how much energy is required to either speed something up or move something against a force. So we need energy to accomplish work. But as it turns out, it takes work to increase energy. So if we look at energy and work, they are actually related, intimately related. So if we have work on one side of the coin, we'll have energy on the other side of the coin. It's the same side or different sides of the exact same coin. So these two things, work and energy, play hand in hand. Energy is required to do work. Work is required to increase energy. So we said last time that the units of work was the joule, and the joule is a kilogram meter squared per second squared. And as it turns out, this is the exact same unit to describe energy. Energy is described in joules. And if you remember last time I talked about the joule is not the only unit to measure energy. Another unit to measure work, the joule, I guess the joule describes the amount of work or the amount of effort it takes to speed something up or move something against a force. The calorie is another unit, and on all of our food products, we see that there is a measurement of calories. That can describe either how much work this food will actually give your body, or you can say this calorie describes how much chemical energy is inside this specific food based on how many calories. So a calorie is another unit to measure energy as well. So we can use calories to describe either work or energy just the same way as we can use joules to describe either work or energy. So there are three different types of energy that we are going to look at. There's actually many different types of energy, but all of those specific types of energy can be boiled down into these three specific types: potential, kinetic, or thermal energy. And we're going to look today specifically at potential energy. So potential energy has many different, potential energy, it's called potential energy. Then it must have the potential to do something. What is that something? Well, potential energy describes something that has the potential really to become kinetic energy. And kinetic energy is the energy of motion. So if something has potential, it has the potential to really move. That's really what potential energy is. For most of my life, I guess I thought of potential energy as a stored energy. You can store energy and it has this potential, so you think of it as stored. But I was informed actually several months ago that it's a misnomer to say that potential energy is a stored energy. And for the life of me, I couldn't figure out why till I guess just a few months ago when I was doing some research on stored energy, and I found that one of the ways to store energy, an idea to store energy would be to store it in rotational kinetic energy. So as it turns out, you can store energy in kinetic energy. So I said, I guess that's why stored energy is a misnomer to describe potential energy. But nonetheless, I still think it's a good way to describe potential energy because in most cases, we're looking at energy that's stored. So if you want to say that this potential energy is stored energy for the sake of your students, I feel like it's still a safe bet, even though it may be a little bit of maybe a wrong way of thinking. But I still think it's a really good way to describe what potential energy is. It's a way to store that energy. Now, there are many different types of potential energy. So here are just a few. I don't know if this is an exhaustive list, but it's a good start. But specifically, we're going to look at the top two, gravitational potential energy and electric potential energy. So let's take a look at this tree and we'll focus in on this apple. This apple has a mass, which means it's being pulled down toward the earth with a force, and we know that force is equal to its mass times the rate of gravitational acceleration g. So this is the force being pulled down onto it. If this apple actually falls from the tree, it will fall the height that it was originally staying. So if we ask ourselves how much work was accomplished by the Earth, work is equal to force times distance. Well, we have a force right here, and we have a distance right here. So work is equal to mg multiplied by h, or mgh. So this is the work that was accomplished by the Earth. Now, if we were to rewind time to just before that apple fell, we would say that the Earth now has the ability to accomplish work on the apple. So this means that there is energy between this Earth and this apple, and we call that potential energy, or specifically gravitational potential energy, because it's the gravitational field that allows, that actually contains that energy. That it's the reason that there is energy. So this is the gravitational potential energy of an apple that's being held at a height h, and that has a mass m. So the question is, who owns this potential energy? Is it the apple, or is it the Earth? Well, if we got rid of the apple, there would be no energy because there's no gravitational force at all. But if we got rid of the Earth and just had the apple, the same thing would happen. There'd be no energy. So when we look at the potential energy, we need to consider both objects. So there's potential energy that exists in the interaction between these two things. And since more than one body is involved, we call this thing a system. Now, a system describes multiple bodies, any number, more than one, that can interact with each other through some type of contact or non-contact force. So this word system is actually not a new word, but a word that we are already familiar with and we use specifically when we talk about the solar system. So the solar system is simply a bunch of bodies of mass that interact with each other through the gravitational field. So gravity is not the only way something can have potential energy, but if we have a little electron and nail it to the board, and then bring in a positive charge and nail that to the board, we can just get an intuitive sense that there's some strain on those tacks, holding these two opposite charges from coming together. Because they're opposite charged, so they're attracted to one another, so there's probably a little bit of strain. And whenever you get that sense that there's like something that wants to come together, this is a dead giveaway that potential energy is involved, because if those two tacks were not there, they would come together. And if they would come together, we'd say that these charges have the ability to do work onto each other, but they're not doing it because they're held together by those tacks. So there's energy, and this energy is called electric potential energy because it's brought on by the electric field that are interacting between these two opposite charges. So if we take a look at a battery, on a battery, there will be some description of the voltage. As it turns out, this term voltage is closely related to electric potential energy. So by related, I mean, would say that electric potential energy is to voltage as force is to acceleration. So the more and more force you have acting on an object, the more it's going to accelerate. The more electric potential energy you have in a battery, the more voltage it's going to have. But as you know from our study in Newton's laws, that if you know the acceleration of an object, it's not quite enough to know what the force acting on that object is. You know there's a force, but you also need to know the mass. You could have a really small object being pushed around by a small force at a really great acceleration. Or if you have a really large mass being accelerated, then you have a really huge force. Likewise, voltage is not enough to know how much electric potential energy a battery carries. If you can recall, there are AAA batteries, there's AA batteries, there's C's and D's, and each one of these different batteries have the exact same voltage. 1.5 volts is a standard voltage, but they do not all carry the same electric potential energy. So though they may have the same voltage, different potential energy. But in the case, if there's a voltage, it means there's an electric potential energy. So if we look at this battery, it has a positive side and a negative side. So if we attach a light bulb to this battery with a pair of metal wires, then it's the electric potential energy that's going to push electrons from the negative side all over to the positive side, causing the light bulb to light up. As electrons pass through the filament in the light bulb, it generates a lot of heat, and that heat causes the filament to glow. So this is an example of a device that converts electric potential energy to light energy. Now, one very important principle that we are immediately starting to see when it comes to potential energy is that objects will naturally move in such a way to lower their potential energy. Objects don't fall up, but they always fall down. Likewise, electrons never go to the negative terminal. They always go to the positive terminal. So here is a very famous photograph of good old Nikola Tesla sitting in his lab, and sparks are just flying all over the place. If we could actually see the electrons traveling, you'd see all these electrons traveling from one spot to the other, we would immediately say, over here is high potential energy, and over here is lower potential energy, because objects naturally tend to move from high to low potential energy. And this principle explains why things fall. All of these objects are simply going to a lower state of potential energy. They find a path and they take it, and as it turns out, that path seems to be straight down or lower towards the ground. So if objects naturally want to go to a lower potential energy, then what does it take to increase an object's potential energy? Well, it takes work to increase the potential energy of any object. So next time you go and try to lift something heavy and are wondering, why is this thing so heavy? Remember this on potential energy, that it takes work to increase the potential energy. So that object simply does not want to increase its potential energy, so it manifests that desire by as weight. So it takes work to lift up that weight, and as it's lifted up, it increases in potential energy. Likewise, if you have two charges that are oppositely charged stuck together, you can imagine the effort it would take to just pull them apart, because it takes work to separate positive and negative charges. But if we go and do the work to separate these charges, then we have potential energy. And energy describes the ability to do work. So now that we have some energy, we have the ability to do something. So here's a water tower, and the work was put in to pump all that water up to the top of the tower. So now there is gravitational potential energy in that water. And we can use this water to give all these homes running water. The key word there is running water. Without that energy, we would not have the running part in running water. We would just have water. So you would turn a faucet on and hear nothing, which would always be sad. But we don't need huge amounts of gravitational potential energy to have running water. Here is a side shot of a toilet, and any toilet with a tank on the back takes advantage of a little amount of gravitational potential energy. And it's this amount of energy that allows us to flush toilets. So the toilet is just really a machine that uses gravitational potential energy to accomplish something. Okay, now moving on to clean renewable energy sources. So if you are anything like me, you may be wondering, if we have the ability to capture energy from the light delivered from the sun, if we have the ability to capture the energy in the wind, then why in the world must we still burn fossil fuels in order to satisfy our energy needs? I mean, why? And the answer to that question is twofold. The first is that it's not always sunny and the wind is not always blowing. So whenever there's no wind and whenever there's no sun every night, we cannot have any energy to light anything. So one would say, okay, well, why don't we just take the abundant energy we take when it's sunny and when it's really windy and we store it? Well, the difficulty is that currently the energy we take from these sources like wind and solar, we either use it or we lose it. And this is probably one of the most frustrating things for engineers or physicists, because we've come up with really clever ways of generating electricity and transferring electricity into, or transferring energy into a way we can actually use it. But it's been a really difficult thing to actually store. And the reason for that is, well, it's energy. And if we remember what energy is the ability to do work. In other words, energy in and of itself does not naturally like to be contained. If we think about the sun is a huge amount of energy that's just bursting forth, and it takes all the gravity of the sun to hold that energy back. Without gravity, it would just blow apart in all of space. So it's hard to wrap vast amounts of energy in a small little box. But it's so silly, because the first thing we learn when we learn about energy is that if you want to store gravitational potential energy, take an object and lift it up, and there you have stored energy. And if you want to release it, release the object and it falls back down towards the ground. So it's one of the simplest problems, yet it's one of the trickiest problems when we consider how do you do it in large quantities. So, but it's a problem we need to overcome, because as it stands right now, whenever there are dips in the wind or the sun, and whenever solar and wind is not available, then that energy is drawn from the power plants, which most of them use some sort of fossil fuel. So they simply supply where wind and solar cannot. So unless we find a way to solve how to store large amounts of energy, then it is unlikely that we will have solar and wind as a viable way to power our world. So it's a big problem, and I just want to talk about some of the solutions because, as it turns out, there are actually plenty of ideas, and a lot of them, some ideas have actually been put into practice. Probably the most used way to store energy is the hydroelectric dam. So this concept is actually pretty simple. If you buy a body of water, then while there's a surplus of energy, you use that surplus to take water from a local source like a river, and then you pump that up into a reservoir, and as the water goes up, then you have stored gravitational potential energy in that water. Then when the surplus of energy is no longer there and you need energy, you can take that water and do the reverse process to turn a generator and produce the electricity. So this is a way to actually store energy. It's probably one of the best ways that we've had for a long time. The biggest problem is not all places are by an available water source. So if a place experiences a huge drought, or if there's no water at all, then this is not a viable option. Another option is lithium-ion batteries. So here's a facility that stores tons and tons of lithium-ion batteries, and energy can be stored in those batteries. There are two big obstacles facing lithium-ion batteries. First is that batteries are not very good at storing vast amounts of energy. So that has slowly improved, but it has improved at a really slow rate. So the only other option is to make that facility huge. And the bigger it is, the more supplies cost and more expensive it becomes to store energy this way. The second problem with batteries is the power problem. So you can theoretically make this facility as big as you want, seeing as though if you have the money and the supplies, but batteries can only give up that energy at a certain rate. So if there is a huge need for energy really fast, then lithium-ion batteries are not the way to go. Power plants are able to deliver a lot of power really fast. So unfortunately, batteries do not have that capability. There is technology and research. There's a lot of research going into improving batteries, but that research has been going on for a long time now, and the progress is much slower than anticipated. So it may be that lithium-ion batteries may not be the solution for our energy storage needs if we want to get rid of fossil fuels. So here's another option, and this one is one of my favorite, but it's perhaps maybe one of the most difficult. But what if you were to take a bunch of water and put it underground through these tubes? So it's a closed system of water. And then you use that water whenever there's a surplus of electricity. You pump that water to pump it all in one space, and you actually cause that water to lift up a chunk of land. So there's now potential energy in this chunk of land. Then when the sun goes down and the wind stops blowing, you allow that land to fall down, and that causes the water to push, and you can get power back out and deliver power whenever the sun is down and the wind stops blowing. So, what's interesting about this hydraulic hydro storage system is that someone calculated that if you have a piece of land that has a height of 2r and a radius of r, so it has a whole diameter of 2r, then you'd get the amount of energy proportional to the fourth power of whatever this distance is. So if this r is a half a mile, then you can get a tremendous amount of energy from this chunk of land. Now the problem is, imagine what we have to go into this construction to build something that can lift up this mammoth rock that was really a mile wide and a mile high. it would be a tremendous undertaking, but you couldn't get really an immense amount of energy from some object like this. But probably not conceivable unless some very creative and some very ingenious engineering methods have been employed. Another really good option is to store potential energy in compressed gases. So here there are many different spaces where inside the Earth there have been lots of gas like helium that has developed and has created a little pocket, and that gas has been taken out and now there's a depleted gas reservoir, so there's like an empty open space just in the Earth, and there's facilities there. So why not turn those facilities into facilities that can actually store energy? So whenever there's a surplus of energy, you can take all that energy to pump in air into these big cavities in the Earth. And then when the sun is not shining, the air is not blowing, you can take all this compressed gas and use that to turn power generators to produce energy to the city, to whatever town. So here's another really interesting way someone's come up with to actually store energy. So whatever the way, it will take a lot of creativity. But I guess when it comes to the problem of storing energy, for later use, it's the only way we can completely get rid of our fossil fuels usage. Unless we can find a way to store the energy we can get from wind and solar, we probably will not be able to move away from fossil fuels. So it's a really important problem to tackle if we want to eliminate fossil fuels. And the reason I bring it up is that if you want it in the classroom, this would actually be a really great problem or project-based idea for students to learn all these concepts in energy, and that can be used in such a way that they can be trying to think about problems. So the project that they would have to kind of come up with, or the problem that they'd have to solve, is on probably a much smaller scale. What are ways that you can store energy and then use that energy a little later and get energy out? So students can come up with all kinds of creative ways, because as I said, we need creative thinkers in order to come up with ways to solve this problem. And what a wonderful opportunity to kickstart that creativity than with some type of project or problem just like this, because it's something that is needed. So that about wraps up everything that I wanted to talk about as far as energy. So right now I just want to open it up to you and see if anyone has any questions they would like to ask about anything concerning anything that I talked about. Okay, so it doesn't look like anyone has any questions, so I'm just going to move on. If you come up with a question later, you can email me and I'll give you my email address later. So next time we're going to jump into the third part, and we're going to talk about kinetic energy. This will be on January 28th, 2016, and it's going to start at the exact same time, on Thursday at 4:30 Mountain Central Time. So if you would like access to the recording or the PowerPoint, you can find those either on the Physics Lab under Teacher Content Training inside Energy One, or you can find these in the resource folders on the Edmodo, on the See the Change USA Edmodo page. Teacher Content Training support. So it doesn't just stop here, but you'll find additional support on the Physics Labs. Within the Teacher Content Training folders within the Physics Lab are a bunch of videos, a bunch of training, so you can access more training on the Physics Lab. If you still need more, you can get more resources on the See the Change USA Edmodo group. This is specifically a place where you can access not only the See the Change staff, but also the teachers working through these units. So really great place to collaborate, ask for help, get ideas, share ideas. So if you're not a member of that, I do highly encourage that you sign up and become a part of that group. And as always, you can email me at vincent.weiss@seethechangeusa.org. And if you have any questions, comments, concerns, do feel free to email me. If you're going through this stuff and you still have more questions and would like to schedule a live session, then you can absolutely do that. Schedule a live session by sending me an email, and we'll set up some live session and we could talk about whatever it is. Or you can send an email to Laura at laura.horvath@seethechangeusa.org. So either one of us. If you just want to contact us directly, then you can call us up at 1-888-843-0671. All right, so let me show you, before I let you go, how you can access the See the Change USA Edmodo group through the physics lab. So what I'm going to do is I'm going to share my desktop screen. Open this up. So here, starting at the physics lab, over here we have resources. If you click on resources, let me log in. So starting at the physics lab, if you click on resources, there's this link tab here. Click on links, and here we have a link to the See the Change USA Edmodo account. Click view, and it will take you to a join request screen right here. Since I'm already a member, I don't have an option to join. I can just go to the group. But if you're not a member, it will say send join request. This is if you've created an Edmodo account, you'll come here. But if you've not yet created an Edmodo account, you can easily create one. You will see this page. Click I'm a teacher right here. And all you need is an email address and a password, and they'll set you up with a free account. And the cool thing about Edmodo is that it's teacher, student, and parent facing. So this is also a place where you can have a virtual classroom to complement all the things that's going on in your classroom. So really neat. And after you access that group, there are tons of resources that have been added. All the videos that are in our lessons have been put into a resource folder, so you can access all those videos in one specific place, make it a lot easier. Same with some of the PhET labs. You can access PhET labs there. And then you can also collaborate with the See the Change staff and all the teachers that are teaching through this same stuff. So really neat stuff. So I'm going to come back to this PowerPoint. And if there are no other questions, I needed to delete that slide. And I just want to thank you all for coming, and we will see you next time. All right, bye.